Hello everyone. The first topic in today's lecture is the inversion of unilateral Laplace transform. In general, inversion of Laplace transform can be performed in two ways. Either by using the direct inverse equation we have seen before, x of t equal to 1 over 2 pi j integrating x of s e to the power st ds. And the problem with this equation is that we are integrating with respect to a complex variable s. Therefore, you will need to do complex contour integration, which is usually performed using the residue theorem. This method is out of scope, we will not be using it. The second method is basically by using the known Laplace transform pairs we have seen so far. So far we have seen the following pairs. E to the power at u of t has a transform 1 over s minus a with the real part of s larger than a. This is the region of convergence. And we have a right-sided signal with a right-sided ROC. And minus e to the power at u of minus t, which is a left-sided signal, has a transform 1 over s minus a with the real part of s less than a. So we have a left-sided region of convergence. And the Laplace transform of delta of t is 1. And of course, if we apply the differentiation in time domain property and we differentiate the impulse, we will get the first derivative of impulse, which is denoted by delta 1 of t. It will have a transform of s. Of course, if we're talking about the unilateral Laplace transform, we can ignore the second entry over here, the one in red, which has a left-sided signal, because in unilateral Laplace transform, we're performing the integration starting from 0 up to positive infinity. But in general, when we do the inverse of bilateral Laplace transform, we will need all these pairs. So the idea is that if we have a function x of s, for which we need to do the inverse Laplace transform. If we can express x of s as a summation of constants and terms in the form 1 over s minus constant, then we can use this table to map every term, like 1 over s minus a, in time domain as e to the power at u of t. If we have a constant, it can be mapped in time domain to delta of t, and so on. So, in the study of LTI systems, which are described by integral differential equations, we frequently encounter Laplace transforms that are a ratio of polynomials in S. Usually you will see this form, x of s expressed as a rational function, as a ratio between two polynomials. In the numerator we have a polynomial of the variable s of order m, and in the denominator we have another polynomial of the variable s, and it has order n. In this case, the inverse Laplace transform is obtained by expressing x of s of this form, a rational function, as a sum of terms for which we already know the time domain function. And this can be done using partial fraction expansion. So, if x of s is an improper rational function, what does it mean to have an improper rational function? It simply means that the order of the numerator polynomial is larger than or equal to the order of the denominator polynomial. In this case, it's called improper rational function. And before we can do partial fraction, first we need to do long division in order to transform it into proper rational function, and then we can do partial fraction. Then we can apply partial fraction on the proper rational function we have, and then we can do the inverse Laplace transform using the lookup table we have seen before. So the first example we have over here, we need to find the inverse Laplace transform of this function. X of s is equal to ratio between two polynomials. The polynomial in the numerator is of order 1, and the polynomial in the denominator is of order 3. So as you can see, it is actually a proper rational function. So in order to do the inverse Laplace transform, we need to do partial fraction. That is to express x of s as follows, as a summation of a1 over s plus 1 plus a2 over s plus 2 plus a3 over s plus 2 all squared. As you remember from mathematics, in doing partial fraction, if the factor in the denominator is of the form s plus 1 or s plus constant, the corresponding partial fraction would be constant over the factor we have, s plus 1. And if we have a repeated pool like this one, s plus 2 all squared, the corresponding partial fraction would be constant over s plus 2 plus another constant over s plus 2 all squared. We have seen this in mathematics before, how to do partial fraction. Next, we can very easily compute the constants a1, a2, and a3. We will find that a1 is equal to 1, a2 is equal to minus 1, and a3 is equal to 2. Next, we can use the lookup table we have seen before in order to do the inverse. And here we will be using the linearity property. Since x of s is a summation of 3 terms, and since Laplace transform is a linear transform, we can actually do the inverse for every term individually and then add the corresponding time domain signals. So the first term is 1 over s plus 1. Going back to the table over here, it's very similar to this term, 1 over s minus a, where a will be minus 1 in this case. So the time domain signal will be e to the power minus t u of t. So the first term we have, 1 over s plus 1, will have the inverse e to the power minus t u of t. The second term over here is 1 over s plus 2. Going to the lookup table, you compare it, you can find it's very similar to this one, where a is equal to minus 2. And in this case, we'll be having the inverse Laplace transform of e to the minus 2t u of t. And in this case, as you can see, 1 over s plus 2 will have the transform e to the minus 2t u of t. We have a mistake over here. It should be e to the power minus 2t. And the third term we have over here is 2 over s plus 2 all squared. In order to compute the inverse Laplace transform for this term, let's go to our whiteboard over here, and we already know a transform which is e to the power at u of t that has a transform of 1 over s minus a. And let's apply the differentiation in s domain property. The property says if we differentiate in s domain, we multiply in time domain by minus t. So in this case, we will be having minus t e to the power at u of t with the transform equal to the differentiation in s domain of 1 over s minus a. And doing the derivative of a rational function, we start by squaring the denominator, and then we take the derivative of the numerator, which is 0 in this case, multiplied by the denominator, minus the derivative of the denominator, which is 1 in this case, multiplied by the numerator. So we will get a term of the form minus 1 over s minus a squared. And now we can see that the term we have over here, which is 1 over s plus 2 all squared, is very similar to this term, s minus a all squared. And a here will be minus 2. And of course, the negative sign here will cancel out with the negative sign here. So we can simply say that 1 over s minus a squared has a transform t e to the power at u of t. And in this case, since it's s plus 2, a will be minus 2. And the inverse would be of this form, t e to the minus 2t u of t. And now using the linearity property, we can get the inverse Laplace transform x of t as a summation of the 3 terms we have computed so far. So the main idea here is to express any x of s we have, which is usually in the form of a rational function, as a summation of this kind of terms, constant over s minus a, constant over s minus a squared, or constant like just a constant or s, and so on. And using the table we have over here, we can do the inverse for every term individually, and next we can use the linearity property to add them together. Moving on, in this example, we need to find the inverse Laplace transform of the following function, x of s equal to ratio between two polynomials. The polynomial in the numerator is third order, the polynomial in the denominator is second order, so as you can see, it's an improper rational function. And before we can do partial fraction, first we need to transform it into proper rational function by using long division. So starting with long division, dividing 2s cubed minus 9s squared plus 4s plus 10, which is the numerator, over s squared minus 3s minus 4, which is the denominator. We divide 2s cubed over s squared, which will give us 2s. And then we multiply 2s by the denominator over here, which will give us 2s cubed minus 6s squared minus 8s. Now we can subtract these. 2s cubed will cancel out and we will get minus 3s squared plus 12s plus 10. Then we divide minus 3s squared over s squared, which will give us minus 3. Multiplying minus 3 by the denominator, we will get minus 3s squared plus 9s plus 12. Subtracting again, minus 3s squared will cancel out and we will end up with 3s minus 2. So 2s minus 3 is the result of the division, and 3s minus 2 is the remainder. So x of s can be expressed as 2s minus 3 plus the remainder we have 3s minus 2 over the denominator. Now we have a rational function that is proper. The numerator is of order 1 and the denominator is of order 2. So now we can do partial fraction. So now we can factorize the denominator into terms like s plus 1 times s minus 4. And now we can do partial fraction. So 2s minus 3 plus constant over s plus 1 plus another constant over s minus 4. And computing the constant is a straightforward task, so we'll get this 4. Now we can use the table we have to do the inverse. So the term s is basically corresponding to a time domain signal, which is the first derivative of an impulse, denoted as delta 1 of t. So here we have the first term is 2 delta 1 of t minus 3 delta of t, because a constant over here, like just 1, will give us delta of t, so 3 will give us 3 delta of t. And 1 over s plus 1 is similar to 1 over s minus a, where a is minus 1, so we'll get e to the minus t u of t. And here it's s minus 4, so a is equal to 4, so we'll get e to the 4t u of t. So here we have applied first long division, then partial fraction, and then we use the linearity property and the lookup table to get the inverse of every term individually and add them together in time domain. The next example, we need to find the inverse Laplace transform of this function. X of s is equal to 4s squared plus 6 over s cubed plus s squared minus 2. It's a rational function, a proper rational function, because the numerator is of order 2, the denominator is of order 3, so we do not need to do long division. We'll start with partial fraction right away. In order to do partial fraction, we need to factorize the denominator first. So let's move to our whiteboard over here. The denominator we have is s cubed minus s squared minus 2. Using your calculator, you can easily find the roots of this polynomial to be 1 and minus 1 plus minus j, which means that this polynomial can be expressed as s minus p1 times s minus p2 times s minus p3. As you can see, p1 is real valued, p2 and 3 are complex conjugate pools. So x of s can be expressed as constant over s minus p1 plus another constant over s minus p2 plus a third constant over s minus p3. And I will leave computing the constants for you guys. I will just give you a hint. Since p2 and p3 are complex conjugate to each other, b and c will also be complex conjugate to each other. So in this case, after you compute b and c, you should get that b is equal to c conjugate. After computing the constants, we can use the lookup table to do the inverse Laplace transform. So the first term over here, a over s minus p1, will correspond to a time domain signal a e to the power p1t u of t. And the second term, constant over s minus p2, will correspond to b e to the power p2t u of t, similarly for the third term. Since P1 is real valued, its value is 1, so this term is straightforward. For the other two terms, the pools P2 and P3 are complex, so we can use Euler equation to express them in terms of cosine and sine. So e to the power P2t is simply e to the power minus 1 plus jt, which is e to the power minus t times e to the power jt. And e to the power jt is simply cosine t plus j sine t. Similarly, for the pool P3 over here, which is also a complex pool, the complex conjugate of P2, so e to the power P3t is e to the minus 1 minus jt, which will give you e to the minus t cosine t minus j sine t. So these are the main parts solving this problem. I will leave it to you guys, and the final result is over here. It will be of this form: x of t equal to 2 e to the power t times u of t plus 2 e to the minus t cosine t u of t minus 4 e to the minus t sine t u of t. Okay, so moving on, let's talk about the properties of the region of convergence, which means we will go back to the bilateral Laplace transform. As you remember from the previous lecture, for unilateral Laplace transform, we do not need to specify the region of convergence because we are operating under the assumption all signals are right-sided, because the integration starts from 0 up to infinity for the unilateral Laplace transform. But in bilateral Laplace transform, we need to specify the region of convergence. So, what is the region of convergence? It is the region in the S domain over which x of s, the Laplace transform, is finite. In other words, the Laplace transform integral converges to a finite value rather than going to infinity. So this region of convergence, is very important part of computing the Laplace transform. The region of convergence is related to the characteristics of the signal x of t. Depending on x of t, the ROC will be determined. The ROC cannot contain any pools because by definition the ROC is the values of s for which x of s is finite, whereas at the location of a pool x of s goes to infinity. So the region of convergence cannot contain any pools. The region of convergence consists of strips parallel to the j omega axis in the S domain, as we've seen in the few examples we had in the very first lecture, and as we're going to see in the next few examples. The ROC starts and ends at pools, so determining the location of pools will actually help us to get the region of convergence, and knowing the region of convergence will help us get the pools. The ROC starts and ends at pools. So, the very first two examples we have seen in the very first lecture in Laplace transform were like this. E to the power at u of t will have a transform 1 over s minus a, where the ROC was the real part of s is larger than a. In other words, a right-sided signal will have a right-sided region of convergence. And the second example was minus e to the power at u of minus t, which is a left-sided signal, and it has a transform 1 over s minus a, but the region of convergence is real part of s less than a. In other words, a left-sided signal will have a left-sided region of convergence. As you can see over here, this x of t is left-sided, so we'll have a left-sided ROC. Here, x of t is right-sided, so we'll have a right-sided ROC. And as you can see, ROC is consisting of parallel strips to the j omega axis. What about two-sided signals? What if we have a signal that's extending from minus infinity to positive infinity, which we call a two-sided signal? So let's take a look at this example. We need to find the ROC associated with these signals and the bilateral Laplace transform with these signals, x1 of t and x2 of t. As you can see, x1 of t has a component which is right-sided multiplied by u of t over here, and another component which is left-sided multiplied by u of minus t. Similarly for x2, so these two signals, as a matter of fact, are two-sided signals. So let's move to our whiteboard and try to solve this example. So the first function we have is x1 of t, which is equal to e to the minus 2t u of t plus e to the minus t u of minus t. And here we have a term which is a right-sided signal plus another term which corresponds to a left-sided signal. And here we can use the linearity. You can compute the Laplace transform of the first term and then add it to the Laplace transform of the second term. So x1 of s will take the form, the first term will be 1 over s minus minus 2, which is s plus 2, and the second term will be minus 1 over s minus minus 1, which is s plus 1. And the region of convergence for this term, because it's a left-sided signal, it will be a left-sided ROC, which is basically the real part of s less than minus 1. Whereas the ROC for the first term, because it's corresponding to a right-sided signal in time domain, it will be a right-sided ROC where real part of s is larger than minus 2. So what is the region of convergence for x1 of s? So let's go to the s domain over here, sigma, and the imaginary axis is j omega. And as we can see, we have two pools. One pool located at minus 2 and the other pool located at minus 1. And the ROC for the first term is simply real part of s larger than minus 2. So I can start shading the ROC as follows. So this is minus 2 and the ROC is simply right-sided. Real part of s larger than minus 2. But the ROC of the second term is that real part of s is less than minus 1. So it goes like this. So the region of convergence of x1 of s is the intersection of the two ROCs. So as you can see over here, this region starting at minus 2 and ending at minus 1 is the intersection between the two regions of convergence. So the region of convergence, the new region of convergence would be the real part of s larger than minus 2 and less than minus 1. And as you can see, it's actually a strip that's basically parallel to the j omega axis. So what about the second function we have over here? The second function we have is x2 of t equal to e to the minus t u of t plus e to the minus 2t u of minus t. So let's move to our whiteboard over here. So we have x2 of t equal to e to the minus t u of t plus e to the minus 2t u of minus t. Again, we will be using the linearity property, so we can write x2 of s as summation of two Laplace transforms. The Laplace transform of the first term will be 1 over s minus minus 1, which is s plus 1. And the second term, since it's left-sided, it will have a transform minus 1 over s minus minus 2, which is s plus 2. The region of convergence for this term will be left-sided, which means real part of s less than minus 2. Whereas the ROC for the first term, since it's corresponding to a right-sided time domain signal, it will be right-sided ROC. That is basically real part of s larger than minus 1. What about the ROC for x2 of s? It will be the intersection of these two ROCs. So in the s domain, this is sigma, this is j omega, and we have two pools. One pool located at minus 1 and the other pool located at minus 2. And as you can see, the first ROC is basically real part of s less than minus 2, which is this shaded region. Whereas the ROC for the first term is real part of S larger than minus 1, which is this region. So, as you can see over here, there is no intersection between the two ROCs. There is no part in the S domain that would satisfy both conditions at the same time. That's why we say that the region of convergence of x2 of S is phi, which is the empty set. And therefore we can say that x2 of S, which is the Laplace transform of x of 2 of t, does not exist. It does not exist basically because there is no ROC in which this expression for x2 of S is valid. For this expression to be valid, we need a region which satisfies these two conditions, but these two conditions are contradicting. The intersection of these two ROCs is empty set. So let's move back over here. So this is the region of convergence for x1 of t. So we have an intersection between minus 2 and minus 1. But for x2 of t, we do not have any intersection, and therefore the ROC is an empty set and x2 of S does not exist. So this would be x1 of S, 1 over S plus 2 minus 1 over S plus 1, as we've seen before. But we can say that the Laplace transform of x2 of t does not exist because the ROC is empty set. Let's move to this example over here. We need to find the inverse Laplace transform of this x of S, which is a rational function, ratio between two polynomials. The numerator is first order, the denominator is third order, so it's already a proper rational function. And here we have a region of convergence specified as follows. Real part of S is between minus 1 and plus 1. And this kind of ROC tells us that we have a two-sided sequence. Because so far we've seen if we have a right-sided signal in time domain, we'll be having a right-sided ROC. If we have a left-sided signal in time domain, we will be having a left-sided ROC. And if we have a two-sided signal in time domain, we might be having either no ROC and x of S does not exist, or we have an ROC between two pools, as we've seen in the previous example. So let's move to our whiteboard over here. So we have a function x of S of this form, and the ROC is specified to be the real part of S between minus 1 and 1, and the function we have here is a proper rational function. So we can do the partial fraction right away. So we can write x of S as a constant a over the first term, which is S plus 1, plus another constant b over S minus 1, plus a third constant c over S plus 2. And now we need to do the inverse transform. We need to find x of t. But before we do so, let's try to draw the region of convergence and see what kind of information we can extract from it. This is sigma, this is j omega. And as you can see, we have three pools in this case. One pool at minus 1, a second pool at 1, and a third pool at minus 2. And we're told to work for the ROC extending from minus 1 to plus 1. So this is the ROC we're interested in. So for this ROC, let's consider the first term we have over here. This term has a pool located at minus 1. So let's go to the pool located at minus 1. So as you can see over here, the ROC we are solving for is considered right-sided with respect to this pool. So again, at this pool at minus 1, the ROC we're solving for is considered right-sided. So the term over here would be a right-sided signal in time domain, because if you remember, having a right-sided ROC means we have a right-sided sequence in time domain. So A e to the minus t u of t. Now for the second term, the pool in this term is located at 1. So going back over here, we have a pool located at 1. And the ROC we're solving for is considered left-sided with respect to this pool. Left-sided means we need to choose the left-sided signal in time domain, which will be of this form, minus b e to the power t u of minus t. And similarly for the third term, we have the pool here is located at minus 2. So going back over here, the pool is located at minus 2, and for this pool, the ROC we're solving for can be considered right-sided. Right-sided with respect to this pool at minus 2, so we will select the right-sided signal in time domain, which is c e to the minus 2t u of t. And of course you can compute the constants a, b, and c very easily, but the important part here is for you to choose the correct time domain signal, be it right-sided or left-sided, based on the ROC we have. So this example will have a completely different solution if we're working in a different ROC. And as you can see over here, how many ROCs we have. We actually have 4 possible regions of convergences. One region of convergence could be real part of S larger than 1. The second ROC, which is the one we solved for, between minus 1 and 1. A third ROC between minus 2 and 1. And a fourth ROC less than minus 2. So we have 4 possible ROCs. We have 4 possible different solutions for this problem, depending on the ROC we have. So let's go back over here, and as you can see, this will be our final answer over here, as we did on the whiteboard in details. And this will be the ROC extending from minus 1 to plus 1, and again the ROC is kind of parallel strips to the j omega axis. The next problem we have over here, again we have x of s, a rational function, but here this rational function is improper. The order of the numerator is 3 and the order of the denominator is 2. And we're given an ROC, real part of s, less than minus 1, which means we have kind of a left-sided ROC, so we'll be having a left-sided signal in time domain. So let's move to our whiteboard and see how to solve this example. Since it's an improper rational function, we need to start with the long division. So we'll be dividing the numerator we have, which is 2s cubed minus 9s squared plus 4s plus 10, over the denominator s squared minus 3s minus 4. Doing the division, we will get the result of 2s minus 3, and we will get the remainder of 3s minus 2. So x of s can be written as 2s minus 3 plus this fraction. And here we have already factorized the denominator into 2 terms. And now we can do the partial fraction, because this fraction now is proper. The numerator is of order 1 and the denominator is of order 2. So it will be 2s minus 3 plus a over s minus 4 plus b over s plus 1. So as you can see over here, we have 2 pools actually. One located at 4 and the other pool located at minus 1. And since we're told to work in the ROC less than 1, so let's try to find the time domain signal like this. So basically the first term is 2s, which will be 2 times the first derivative of impulse delta of t, minus 3, it will be minus 3 delta of t. The first term over here is the pool located at 4. So at this pool, the ROC we are solving for is kind of left-sided, so we need to choose the left-sided sequence over here, which will be minus e to the power 4t times u of minus t. And similarly for the second term, we have over here the pool is located at minus 1. So for this pool located at minus 1, the ROC we are solving for is kind of left-sided. So again, we need to choose the left-sided signal, which will be e to the minus t u of minus t. And this will be the signal x of t we have. Again, computing the constants a and b is very straightforward. So if you go back over here, this will be your final answer, which is exactly the same as the one we have found on the whiteboard. Okay, so now we need to talk about the transfer function of LTI systems. If you remember, an LTI system which is characterized by an impulse response h of t and has an input signal x of t, the output from such a system can be computed using the convolution integral. Y of t is equal to x of t convolution with h of t. And now we can use the convolution property of the Laplace transform in order to get y of s equal to x of s times h of s, where y of s is a Laplace transform of the output y of t, and x of s is a Laplace transform of the input x of t, and h of s is a Laplace transform of the impulse response h of t. And h of s is known as a system transfer function. It's also known as the eigenvalue. So we can find h of s as y of s over x of s. We can get the system transfer function by dividing the Laplace transform of the output signal over the Laplace transform of the input signal, y of s over x of s. h of s is the Laplace transform of the impulse response h of t. h of s is known as a system transfer function. And as you remember from the previous chapter, the system properties such as causality and stability are closely related to the impulse response h of t, and hence closely related to the system transfer function h of s, since h of s is the Laplace transform of h of t. In other words, we can learn about the system properties such as causality and stability from h of t and from h of s. And also h of s is closely related to the differential equation describing the system we have. Therefore, we can start by an LTI system described by a differential equation. And applying the properties of the Laplace transform, we can transform this differential equation into equation of s and s squared and s cubed and so on, from which we can get h of s, from which we can get h of t, and learn about the system properties such as causality and stability. So let's see this example we have. An LTI system is described by this differential equation, d2 by dt squared y of t plus 3d by dt y of t plus 2y of t equal to 2d by dt x of t minus 3 x of t. And here we will apply the differentiation in time domain property of the Laplace transform, which simply says that differentiation in time domain is equivalent to multiplying by s in s domain. So the first derivative multiply by s, a second derivative in time domain multiply by s squared. And of course we had some initial conditions in the property, and as we've said before, we will assume that there is no initial conditions in most of the problems we're going to deal with in this module. So let's move to our whiteboard over here. So we have the second derivative of y of t plus 3 times the first derivative of y of t plus 2y of t equal to 2 times the first derivative of x of t minus 3x of t. Applying the properties of Laplace transform, we will be having s squared times y of s plus 3s times y of s plus 2y of s, and here we're applying the linearity property and the differentiation in time domain property. This will be equal to 2s times x of s plus minus 3x of s. And now we can simplify this equation in order to obtain y of s times s squared plus 3s plus 2, which will be equal to x of s times 2s minus 3. And now we can get the system transfer function h of s as the ratio between y of s over x of s. And this is due to the convolution property. So we can see that the system transfer function will be like this. Here we'll be having s squared plus 3s plus 2, and here we'll be having 2s minus 3, and this will be the system transfer function. As you can see over here, this will be our system transfer function. So starting with a differential equation, we can obtain h of s, and from h of s we can get h of t, and we can get the pools and zeros and ROC, and as we're going to see in few minutes from now, we can learn about the system properties from these things. Here we are given a differential equations and we need to find the system transfer function, so it's very straightforward. I will leave it to you guys as an exercise. So you have the final answers over here, and again here we have the other way around. We have a system transfer function and we need to find the differential equation. Again, it's very straightforward. You have the final answer. So I want you guys to try solving these two problems. So now let's try to relate the system transfer function and the system properties. So remember, the impulse response h of t is the inverse Laplace transform of h of s, or h of s is the Laplace transform of h of t. So for causality, the impulse response of a causal system is 0 for t less than 0. So h of t must be 0 for t less than 0 for a system to be causal. Therefore, we know that for a causal system, h of t is a right-sided signal, so h of s would have a region of convergence which is also right-sided. So the ROC of h of s must be right-sided, starting from a certain pool going to infinity. And for stability, if you remember, the impulse response of a stable system must be absolutely integrable function. That is, it must be a decaying function. Therefore, we know that a system is stable if the region of convergence includes the j omega axis. So we can learn about a system if it's stable or not if its ROC includes the j omega axis. If the ROC includes or contains the j omega axis, then the system is stable. If it does not include j omega axis, the system is not stable. There is a mathematical proof for this property, but it's kind of out of scope. We'll skip it for now. So I need you guys to know, if you want to have a causal system, the ROC must be right-sided. And if you have a stable system, the ROC must include or contain the j omega axis. So in this case, we have a pool located over here, let's say at -1. And if the ROC is looking to the right, if it's a right-sided ROC, then j omega axis will be included in the ROC and this system would be stable and causal. But over here, this pool, let's say located at 1. If we have a causal system, the ROC must be right-sided. So in this case, j omega axis is not included in the ROC, so the system is not stable. And if the ROC is left-sided, the system will not be causal, but it will be stable. So, for a system to be both causal and stable, all pools must be in the left half plane of the S domain. Again, for a system to be both causal and stable, all pools must be in the left half plane of the S domain. In other words, the real part of the pool must be negative. So as you can see over here, all poles are located in the left half plane. We will select the rightmost pole and we will start the ROC at the rightmost pole extending to the right. In this case, the system will be causal because the ROC is right-sided, hence giving us a right-sided signal in time domain, and it will be including the j omega axis since all poles are in the left half plane. So in this example, we need to find the impulse response and decide if this system is causal or stable or not. So h of s is equal to 2 over s plus 3 plus 1 over s minus 2. We need to find the impulse response in two situations: A, assuming a system is stable, and B, assuming a system is causal. And we were being asked, can this system be both causal and stable at the same time? So let's move to our whiteboard and try to solve this important example. So here we have h of s equal to 2 over s plus 3 plus 1 over s minus 2. So basically we have two pools. One pool located at minus 3 and the other pool located at 2. So first we need to find the impulse response, but in order to do the inverse Laplace transform we need to find the ROC. In the first situation, we're told to solve if the system is known to be causal. So for a causal system, we know that the ROC must be right-sided. So for a causal system, the ROC would be larger than 2. So in this case, we can find the inverse Laplace transform very easily. X of t will be equal to the first term we have 2 over s plus 3. The pool is located at minus 3 and the ROC we're solving for can be considered as right-sided, so we'll be having 2 e to the power minus 3t times u of t plus the second term we have 1 over s minus 2. For the pool located at 2, this ROC can be considered right-sided as well, so it will be e to the power 2t times u of t. And as you can see over here, it's right-sided, so it's causal, but the problem here will be with this term. As t goes to infinity, e to the power 2t will go to infinity, so it's kind of a growing exponential, which means the system is not stable. Of course, this is h of t, not x of t, it's impulse response. So an impulse response will be growing exponentially and hence it will not be stable. The second situation we have, if the system is known to be stable and we need to find the impulse response. So for the system to be stable, the ROC must include the j omega axis. In this case, the ROC would be between minus 3 and minus 2. So in this case, ROC would be the real part of S larger than minus 3 and less than 2. And in this case, we will be having a two-sided signal. So the first term we have 2 over s plus 3. The pool is located at minus 3 and the ROC is kind of right-sided, so we'll be having 2 e to the minus 3t u of t, which is a right-sided decaying exponential. And the second term is 1 over s minus 2. The pool here is located at 2, which means the ROC we're solving for is left-sided, so we'll be having minus e to the power 2t u of minus t. So it's a left-sided signal, which means the system here will not be causal because h of t has a left-sided component. So here the system is not causal, and when the system was known to be causal, it will not be stable. And of course here when the system is causal, the region of convergence must be right-sided, so the real part of S is larger than 2. So as you can see over here, this system cannot be both causal and stable because all poles are not located on the left half plane. For a system to be both causal and stable, all poles must be located in the left half plane of the S domain. So as you can see over here, solving for a system to be causal and stable, we will get two different impulse responses. In the first situation, when the system is known to be stable, we will be having e to the minus 3tu of t and e to the power 2tu of minus t, which is a two-sided signal, so it's not causal. And in the second situation, when the system is known to be stable, it's not known to be causal, it will be e to the minus 3tu of t plus e to the power 2tu of t. It's causal, it's right-sided, but it's not stable. And of course, the system cannot be both causal and stable because the poles are not located in the left half domain. We have a pole located at S equal to 2. And here we have a problem. I want you guys to solve it. We have two systems described by two differential equations. So we can easily transform these into h of s. And from h of s we can find the impulse response, assuming the system is causal and stable. And we can determine if the system can be both causal and stable at the same time. In this example, we are given this differential equation and we need to find the transfer function of the inverse system, and if this system is causal or stable. We need to determine if this system is causal and stable. What is the inverse system? The inverse system is a system whose transfer function is 1 over a transfer function of this system. So let's start by finding the transfer function of this system we have over here. So applying the linearity and the differentiation and time domain property, we'll be having s times y of s plus 3 y of s equal to x of s times s squared plus x of s times s minus 2, which will be of this form. So the transfer function of this system will be h of s, s squared plus s minus 2 over s plus 3. The inverse system is a system whose transfer function is 1 over h of s. So h inverse will have the form 1 over h of s. So it will be s plus 3 over s squared plus s minus 2. Factorizing the denominator, we'll be having s minus 1 times s plus 2, which means we have a pool located at 1, another pool located at minus 2. So this system cannot be both causal and stable because we have pool located at 1. Again, for a system to be both causal and stable, all pools must be located in the left half plane. This is a problem where you have the impulse response and you need to find the transfer function of the inverse system. So you will apply Laplace transform, find h of s, and then h inverse is 1 over h of s. And here you have h of s given, and you need to determine whether the system described by these transfer functions can be both causal and stable. So you will find the location of the pools. If all pools are located on the left half plane of the S domain, so the system can be both causal and stable. And in the second part, we need to determine whether the inverse system can be both causal and stable. So again, the inverse system will have a transfer function 1 over h of s, and you can find the location of the pools of the new system, and you can decide whether the system can be both causal and stable. So the key point here, if you want the system to be causal, the ROC must be right-sided, which means the time domain signal h of t, the impulse response, must be right-sided. And if you want the system to be stable, j omega axis must be included inside the ROC. So if you want the system to be both causal and stable, all poles must be located on the left half plane in the S domain.